Let me give you this map.
You should set the alarm for 5 minutes before the end so I can hand stuff back. Turn the camera on. All right. So let's start out with any questions. What is that, the rook?
Okay. So on our lab, when we're calculating the momentum and torque.
Momentum?
Yeah. So do we do it? So I know you told me to find the moment arm a certain way for part C. Would it be the same for part D and E?
It gets a little bit trickier for the one that's at an angle. So we'll address that when we talk about the ladder problem.
Okay.
But for the places, the ones where the meter stick was horizontal, then yes, it's the same technique. Brooke, oh, that's right.
You're fine. I was working on the chapter 8 mouse move set, and question 3 says a ball is bounced against a wall traveling at positive 30 meters per second, like with a velocity of 30 meters per second, and then after the wall, it's negative 30 meters per second, and it's asking for the impulse. So since impulse is just change in momentum, is it negative 60 meters per second? Or is there like math involved?
There's mass involved. It's mass times, so impulse change in momentum, so final momentum minus initial momentum. And so mass times initial velocity would be, I can figure out what the mass was.
It's 1.9.
Of course, I didn't do an integer. So 1.5 kilograms times 30 meters per second.
Okay. You said it was the change in momentum?
Yes.
Okay. Okay, yeah.
So you will end up with a
30.
negative impulse.
Okay, gotcha. Because it's 30, negative 30. So multiply that by the mass, and that's the impulse.
Yes. I'm going with the spirit of what you said, not the exact words.
Okay. Because impulse is the force times the change in time.
Yes, but I didn't give you enough information to know to solve it that way.
Okay.
There's two ways of finding impulse. If you know the force and time, you do it that way, and if you know mass and change in velocity, you do it that way.
Okay.
And change in time, that's just how much time the interaction took place.
Cool.
So there are times I'll give you this information and then ask you to find that, and other times I give you this information and then ask you to find that. So if I then said, if the interaction took place over 0.1 seconds, what was the average force? And so then you would take this that you'd already found.
Divided
by
by
here.
time, yeah.
Other questions? Again, just to confirm. Yep, that's right. All right, so let's take a look at the ladder problem. Guess I need to give some information here. So mass of person, will make 70 kilograms. Mass of ladder, which is 10 meters long, is 10 kilograms. There is friction down here. Since all I care about is whether it slips or not, then all I gave was the static coefficient. I could give the kinetic coefficient, and that is information that we will not use at all, but let me throw it in there anyway, just to make it look more confusing, so that it looks like you have to decide which one to use. But we'll look at static. something that's less than 0.4. And I gave the angle there, all right. So the questioning is, how far up the ladder do we go before it slips, which might give some impression to occasionally to students going, well, it's gonna slip, so therefore we're using use of K. But recognize, when I'm asking how far up the ladder does the person go before the ladder slips, I'm asking how far up can he go and it's still not slip. Because the point at which it starts to slip and the last point where it wasn't slipping are too close to each other that, again, just using the static. We're going to go through the exact same steps as we have been all along. Force diagram. Now we're sophisticated enough that I don't have to draw in everything. All I really need is the ladder here. What are the forces acting on the ladder?
Gravity pulling it down, normal force pulling it up. There's another force,
Right, so gravity pulling it down.
normal force acting up on it at the, yeah.
Friction acting to the right on the bottom of the ladder.
And there's this other force of this person. I guess it's just the person's gravity though, or weight.
Anyone want to nitpick that besides me? Anyone willing to nitpick it?
Is it the normal force of the person acting down the ladder?
Yes, it's the normal force. Now, if he's just standing there, the normal force and his weight would be equal.
But he's moving, okay.
So technically, person, normal force, weight of person. And then there's a weight, because the weight is between him and the earth. But if he's in equilibrium, those are equal in magnitude to each other. So I'm just gonna go ahead and write Y equals WP.
Wouldn't it not be equal to the weight because it would be acting at an angle?
Another question of why is this not like this box on ramp or person on ramp problem?
Because we're focusing on the person instead of the ladder.
That's not the issue here. How is the ladder different from a ramp?
Because there's like
You're still standing
Rungs.
straight up.
on the ladder.
Yeah.
Right. Okay.
At least when I walk on ladders,
Yeah, yeah,
I'm
yeah.
still standing straight up.
Okay.
If it were a person on ramp, it would be, I would agree with where you were going with that. We are missing one more force.
Normal force against the right wall?
Yeah. So it's not the same as these two here, so I need to put in different subscripts. Oh, I left subscripts off, so we'll just put Y sub P here, Y sub P. I'm gonna do Y sub V for vertical and Y sub H for horizontal. If you don't like those, come up with your own. But Y sub V. 1 and 2 probably would have made more sense, but I didn't do it. All right, so we have our forces here. Direction of acceleration.
The what?
Why?
The acceleration of the ladder.
Yes.
Well, the ladder's not accelerating as of right now, so.
Yeah. We're working on this problem. I can understand when it starts to slide, yeah, the ladder's gonna be basically slipping off that way. The acceleration actually would probably be sort of at an angle. They're not straight down and not straight left, but sort of at some strange angle like that. But you're lucky, fortunate, or blessed that I'm not asking you to find the acceleration once it starts to slip. Because that is a much more difficult problem. So without it accelerating, or with the acceleration of 0 meters per second squared, How do you want to set up the coordinate system?
I guess like normal, like earth coordinates, like up is positive, right is positive. Since nothing's moving, I don't see a need to really switch anything around.
All the forces are horizontal and vertical, it just makes sense to stick with horizontal and vertical, and then K's coming out, because this is a three-dimensional problem, even though it doesn't look like it on the surface here. So nothing to decompose, because we chose coordinate system properly, or conveniently. Equations of motion. How many equations of motion will we have?
Just two.
There'll actually be a third one, but let's get the two down. What are the two?
Y sub B minus Y sub P minus W equals MA.
We can do better than that. I'm gonna make this W sub L, just. Because I just picturing at some point like dropping subscripts completely and then suddenly I've got mixed up W's.
Oh, is it massive ladder? Is that what you're looking for?
It would be massive ladder times
So.
Are you getting at 0?
Yeah. 0.
It's okay. We haven't determined whether there's an well, the acceleration is equal to 0, you did say that.
Yeah, because it's not, so we're looking at that point while it's still not slipping.
Okay.
Then,
How did you get the YH at the top of the?
that's because it's leaning against the wall right here. The wall is pushing it to the left.
We've determined that acceleration is 0, but how do we know if that's for like the vertical or horizontal? Like this first equation of motion that you set up is only concerning vertical forces, so how do we know that the acceleration goes, the 0 goes with that equation?
It is completely static here. The ladder is not slipping for for the part of the problem we're solving.
So is so the acceleration for the other one concerning like friction and the horizontal normal force, that's also gonna be 0.
Correct.
It's just gonna be the third equation of motion of the person that's gonna be different.
No, they'll all be equal to 0.
Okay.
It's in linear equilibrium, which will count for the first two, and it's rotational equilibrium for the third one.
Okay.
All right, then,
Why is that normal force only going to the left side?
oh, you thinking there should be something going,
Because of the wall.
Yeah, if it's going like, if you have a normal force up for the person, we have one for down too.
oh, is it an issue of the fact that I didn't do the wall piece of it? Because there is, if the wall's here, there is a force acting that way on the wall. I just was leaving the wall off. Okay. Other questions at the moment? Lisa?
What did you write down there with YP equals WP?
Oh, YP equals WP. Because technically, the force that he exerts on the ladder is his normal force, not his weight. But if he's in equilibrium, then the normal magnitude of the normal force and the magnitude of the weight are the same thing, or equal.
Okay.
Which means that as he's walking up this ladder, he is walking up very slowly. He's not changing his velocity. Now, normally, if I step up on this chair, I'm pushing down on the chair in order to bring myself up. So I'm not in equilibrium at that point as I'm lifting it, as I'm lifting myself up. We are making the assumption that he is very carefully walking so slowly, incredible muscle control, that his acceleration is so small as he's walking up the ladder, and I don't have the muscle control to do that, that he is close enough to equilibrium, that these forces are equal in magnitude. Now, if he's running up, then the equilibrium thing would not be true, and it becomes, well, the ladder will slip sooner. And you can try this at home. All you need is a frictionless wall and to know the coefficient of friction on the ground.
Suggestion for our next lab?
See how far up you can go until the whole ladder falls out underneath.
Actually, a lot of ladders have rollers up here to sort of make it somewhat frictionless up there. One of the reasons why we make this frictionless over here is that if I throw an extra friction in here, so there's a friction acting upwards, because again, the ladder wants to slip like that. Then we get into a situation of there's static friction, so we know what the, if I knew the coefficients, I know what the maximum value is, but if the ladder's not slipping, I don't know what the actual individual values are. If it needs, for example, if it needs 30 newtons not to slip between these two, I don't know if it's split equally or differently, how it's split. And so, the classic physics problem, you make this zero. And a rationalization is a lot of ladders have rollers at the top to make this less frictiony. All right, the other equation.
F of S minus Y of H equals 0.
Okay?
And then y sub person minus weight sub person is equal to 0.
Oh, okay. That was not the third equation I was thinking of, but,
What were you thinking?
well, let's solve this what we can, and then we will get to what's missing. Or does anyone see what's missing already? Why this is not sufficient?
Could we not find WL with that?
Oh, we good. We're fine.
Oh,
Does it have something to do with the, displacement of the person? Because where the person is standing influences whether or not it will slip?
Yes. The question that I'm asking is how far up the ladder can the person go? Nowhere in here is how far the person goes. That's what's missing. And for that, we'll need torque, otherwise why do this problem now? All right, so let's at least solve this here. What's next step? Substitution. I have a formula for friction, weight, and weight. So YV minus Y, well, from this I know it's equal to WP, so I'll go ahead and make that substitution. Minus WP minus WL equals 0. Fs equals YH. So YV is equal to MPG plus MLG. And YH is equal to mu SYV. A little bit of rearranging there, but basically substituting in the formulas for weight and the formula for friction. Let's plug and jug. So YV will be $788. Right.
It's the mass of the person, it's gravity, weight of the person plus weight of the ladder.
Yep. I wrote the masses over there.
Okay, yeah.
784.
784. Units?
Newtons.
And so Y sub H, the horizontal normal force pushing the ladder to the left would be 0.4 times 784.
$313.6. Oh, newtons? It's multiplied by friction, so, well, Yeah.
Just looking at constants.
Oh,
The question mark.
all right, so you're removing the question mark from your answer?
Yeah.
Okay, all right, we're good. So I now know that this friction right here and the normal force right here are 313.6 newtons. This is 313.6 newtons. And Y sub V, the vertical normal force here, is 784 newtons. The weight of the ladder, well, the weight of the person is easier, that's 98 newtons. And the weight of the ladder,
70 times 9.8 is 686.
686 newtons. All right. Now we have that question to answer about how far up he needs to go. And so now we get into the more math intensive piece of it, and one more related to why that section of the lab was part D, I think it was, whichever one, D or E, becomes trickier. We need our K equation, because this first one right here that we did up here is the J hat equation. This is our I hat equation, and we need a K hat equation. In other words, torque. I'm going to redraw my force diagram here. It's supposed to be a straight line. So it's 784 acting up, 313.6 acting to the right, 313.6 acting to the left. This is in the middle of the ladder. I'm assuming the uniform ladder here is, ooh, I got those backwards. That's 98. And that's 686. Is that 686?
Why is the weight of the person? Oh yeah, because the person weighs more. Yeah, it's 686.
Okay. So 98 newtons. And then somewhere on here, again, don't know, that's just some distance x of 686. Wow. Okay. For something that is not rotating, where do you pick